Hello everyone, this is our session 9 on indefinite integration. We'll do some special type of integrals today. These formulas will be required for the next exercise. Also, there are a few types of integrations, that is quadratic integration, then trigonometric quadratic equations. So we'll learn these types right now, and then we'll utilize them in the next session, in the next exercise that we will study. Okay, so let us start with the special integrals. Okay, so whatever integrals that we are going to study now requires some kind of substitution. Okay, so what are these substitutions? If you come across terms that is a square minus x square, then you write or you substitute x as either a sine theta, a cos theta. Okay, then if you come across term like x square plus a square, either with root sign, without root sign, you can use this substitution. So what is the substitution for both positive? A tan theta, a cot theta. Okay. Now, when x is negative, substitution is sine theta or cos theta. Okay. And when x is positive, then the substitution is a sec theta, a cosec theta. Okay. And the last one is root of a minus x upon a plus x, or root of a plus x upon root a minus x. If we have something like this, then the substitution is a cos 2 theta. Okay. Now, it's difficult to remember it in one go. But as and when we practice these special integrals as well as numericals on it, then you'll get used to the substitution. Okay. If not, then keep revising through the substitutions so the sums become easier. Okay. Let's begin with our first special integral. Okay. So the first one is integral of 1 upon x square plus a square. Now, if I have this in my integral, 1 upon x square plus a square dx, okay, then its integration is 1 upon a tan inverse x upon a plus c. Okay, now we have to prove this here. For let's say if the sum as is comes as a proof, then you should know how to prove it. So we are going to do the proof as well. When we use it in the sum, we directly use the answer. Okay, that is, we convert the sum into x square plus a square, and we directly write the answer as 1 upon a tan inverse x upon a. A could be any perfect square, like x square plus 4 square, or x square plus 25, that is x square plus 5 square. So you directly write the answer. Okay, that is when we are going to do the numericals. Right now we are doing the proof of this special integral. So let us do the proof. Okay, so let's take the, now this you have to prove that integration of 1 upon x square plus a square dx is this 1 upon a tan inverse x upon a plus c. So let us take a left hand side for us. LHS is equal to integration of 1 upon x square plus a square dx. Okay, and how will we start the sum? So if you could refer to the red box here, if you have something as x square plus a square, what do? We use the substitution x is equal to a tan theta. Okay, so let us use this substitution here. So let's say let x equal to a tan theta. Now if x is equal to a tan theta, what is dx then? Dx will be equal to a sec square theta d theta. Okay, and you also have to write the value of theta. So theta is equal to tan inverse x upon a. So yeah, these three things you will write when you substitute, and then you put it in your LHS. So LHS is equal to integration of 1 upon, what is x? It is a tan theta, so a square tan square theta, okay, plus a square dx. Sorry, d theta we have to write, so not dx now. So that will be a sec square theta d theta. Right, dx value has to be substituted as well. Okay, let's go to the next step now. That will be LHS is equal to integration a sec square theta d theta divided by, now in this you have a square common, so we'll take a square common, tan square theta plus 1. What is tan square theta plus 1? It is sec square theta. Okay, so this will be integration of, one of the a cancels, sec square theta d theta upon a sec square theta. Okay, this cancels out, so we have 1 upon a outside, integration d theta. What is integration of d theta? It will be theta plus c. Okay, now what is the theta value? So let's resubstitute the theta value. So we'll have LHS is equal to 1 upon a, what is theta? Tan inverse of x upon a plus c, okay, which is equal to your right hand side. So we have proved that integration of 1 upon x square plus a square dx is equal to 1 upon a tan inverse x upon a plus c. Okay, now this can come as a proof in a number format. That is, in place of a you will have say 4 square, 5 square. So you directly write the answer as, let's say if we had x square upon x square plus 5 square, okay, dx. So the answer would be 1 upon 5 tan inverse x upon 5 plus c. Directly you can write the answer. So that's why I said it's difficult to remember all these formulas in one go. You'll keep solving sums in these and you keep revising the formulas. It becomes easier to remember. Clear? This was the first special integral. Let's move to the second one now. Okay. So the second one is integration of 1 upon, now we finished x square plus a square. Let's do x square minus a square dx is equal to 1 upon 2a log of x minus a upon x plus a. Now this is a mod sign. Normally you take positive values of the answers that you get. That's why that mod sign is given. 1 upon 2a log of x minus a upon x plus a plus c. We have to prove this. Okay, so first let us go to the substitution column, the red column. We have x square minus a square. The substitution should be a sec theta or a cosec theta. Okay, so let us begin. Okay, now in this kind of sum, there is a different method of proving as well. So I'm going to show you that method. LHS is equal to integration of 1 upon x square minus a square dx. I'm going to use the factorization method. That is, I'm going to use x minus a, x plus a, okay, dx. Now if you can see the right hand side, it requires x minus a in the numerator. Okay, also if you could work it the reverse order. Work it the reverse order means what? What do I require on the right hand side? Log of say a upon b, that is log of a minus log of b is what I require. X minus a minus x plus a. So I'll put this over here in place of 1. Okay, let's see, does that work? Integral of x minus a minus. Okay, now since this is giving me minus 2a, I want a positive value. So what I'll do is I will write x plus a first. Okay, so we have x plus a first, okay, minus x minus a. Okay, now if I open the bracket, what do you get? X plus a minus x, so x cancels out, plus a, that is 2a is what I am getting in the numerator, which is an extra term. So what will you have to do? You will also have to divide by 2a so that it is nullified. The extra term is nullified. So I'm going to say 2a. In brackets here you can write multiply divide by 2a. Okay, now let's continue. So LHS is equal to 1 upon 2a as it is, integration of the first term is x plus a, okay, divided by x minus a, x plus a, okay. We have a minus sign and we have dx here, so we put dx, integration of x minus a divided by x minus a, x plus a, dx. What did I do? Separated the numerator and given the denominator to each of the terms in the numerator, the factors, okay. Also, integration is separated and 1 upon 2a is still outside. That's a constant, okay. Now, what will be the first term? Log of x minus a, okay, minus log of x plus a, right? And we'll have plus c, okay. So, which we 1 upon 2a log of, since it's subtraction, so it will be x minus a upon x plus a plus c. Clear? So one thing, the c value should remain outside the bracket, otherwise you will, even if you multiply 1 upon 2a into c, it's still a constant, okay, so which will be another constant value. So if you put it inside the bracket, then take it as c1 and then later on you can put it as c. That is 1 upon 2a into c, right, is equal, c1 is equal to c, like this, okay, but I'm keeping it outside the bracket. Clear? So 1 upon 2a log of x minus a upon x plus a plus c, this is your RHS. So what is the identity that we have proved, or you can say special integral that we have proved? 1 upon x square minus a square, is it x square minus a square? Yes, dx equal to 1 upon 2a log of x minus a upon x plus a plus c, okay. Second. Yes. So that is your identity that we just proved. Okay, let's go to the next special integral. Okay, the third one. What we'll do is, after we prove them, we'll take them down all together and write it as a formula list. Okay, so let's do the third one now. So this is integral of 1 upon a square minus x square dx, okay, is equal to 1 upon 2a log of a plus x upon a minus x plus c. Okay, now you can use the exact same method that we have used for the previous proof. What is that method? So we'll take LHS equal to integration of 1 upon a square minus x square dx. Okay. Now since there is 1 upon 2a, what we could also do is just in the beginning only we'll multiply by 2a. Okay. And write the factors here, a minus x, a plus x, okay, dx. Now let's split this 2a to get the factors in the numerator as well. So how would you do this? It will be a minus x, okay, minus a, sorry, a minus x plus a plus x, okay, divided by a minus x, a plus x. Okay, so have we nullified the terms? Let's check. So a minus x plus a is 2a minus x plus x, which will cancel out. So yes, 2a is already intact. There is no extra term that we have added. Okay, so let us separate and write the answer. So we are going to get 1 upon 2a integration of, we put it in a bracket, a minus x divided by a minus x, a plus x dx. Okay, plus integration of a plus x divided by a minus x, a plus x dx. Okay. So we'll have a plus x cancelling out here, minus x cancelling out here, 1 upon 2a, okay, log of x, a plus x plus log of a minus x dx. Okay, divide by minus 1. Now, why is this divide by minus 1? Can you tell me? So, if you remember, we did whenever you take log of any binomial, you have to check whether x has a coefficient. So, here normally x had positive coefficient, so we did not divide by 1. Okay, but here in the second term, it has a minus x. Okay, so we have to divide by minus 1, which will be 1 upon 2a log of a plus x, okay, minus log of a minus x. Okay, now dx, this should be plus c over here because we've taken the integration, sorry, yes, plus c. So now it's a subtraction term, and so we write 1 upon 2a log of a plus x upon a minus x plus c. Okay, so we have proved this for our third type. What is the third type? A square minus x square. Okay, so you're getting 1 upon 2a log of a plus x upon a minus x plus c. Okay, let's go to the next one now, fourth one. Okay, the fourth is integration of 1 upon root of a square minus x square. Okay, dx equal to sine inverse x upon a plus c. Okay, what we can do is in the red column that we have made, okay, okay, we have the root sign here, right, for the fourth one. So what is the substitution that we are going to use? Let's go back to our red column and check. We have a square minus x square in our, so we are going to use x is equal to a sine theta. Okay, let us use x equal to a sine theta for our LHS. So LHS is equal to integration of 1 upon root of a square minus x square dx. Okay, let x equal to a sine theta. Okay, so dx will be equal to a cos theta d theta. Also, theta is equal to sine inverse of x upon a. Okay, let us use the substitution for our LHS. So LHS will be equal to integration of 1 upon root of a square minus, what is x? X is a square sine, x is a sine theta. So we write a square sine square theta. And what is d theta? A cos, what is dx? A cos theta d theta. Okay, so we have integration of a cos theta d theta divided by a square common, so a comes outside, root of 1 minus sine square is root of cos square theta, which will be integration of cos theta upon cos theta d theta. Okay, cancels out. What is integration of d theta? Theta plus c. Let us substitute theta. It will be sine inverse x by a plus c. Okay, that is your LHS, which is equal to your right hand side. Okay, this was the fourth one. Let's move to the fifth one now. Okay, in total there are 7. Okay, I'll do all of them for you so that you can refer to this video whenever you are in doubt why this answer is so or how do you prove it. Okay, so prove that. This is for the fifth one, integration of 1 upon root of x square minus a square. Now we were doing a square minus x square. I used sine theta. When I require x square minus a square, I will use the value of x as a sec theta or a cosec theta. Okay, let us begin. So what is the proof? Equal to log of x plus root of x square minus a square, okay, plus c. So let's take our left hand side. Integration of 1 upon root of x square minus a square. Now since I'm going to get 1 minus something, okay, rather in the previous one we had, yeah, so here we are not going to get 1 minus, we are going to get a trigonometric value minus 1. So that is either sec square theta minus 1 or cosec square theta minus 1. Then I can use an identity. Okay, so how will we substitute it? We'll say let x equal to a sec theta. Okay, so dx is equal to a sec theta tan theta d theta. Okay, yes. Let us put it in the left hand side. So left hand side is equal to integration of 1 upon root of x is a sec theta, so a square sec square theta minus a square, dx is a sec theta tan theta d theta. Okay, now in the denominator, root of a square is common. You take it out and you get 1 upon a. Okay, so LHS is equal to integration of a sec theta tan theta okay d theta divided by a common outside. Now what is left in the bracket? It is sec square theta minus 1, which is root of tan square theta, that is tan theta. Okay, cancels out, a cancels out, so we have integration of sec theta d theta, okay, which is log of sec theta plus tan theta, okay, plus c. Now can you tell me, is this the final answer? It's not, because we have not put it in the form of x. Okay, so let's put it in the form of x. We need to substitute what is sec theta and tan theta. We have an answer for sec theta. Okay, we have to find it out. So let's put it over here. Okay, so we have x is equal to a sec theta. Okay, so we have x upon a is sec theta. So now we have an answer for sec theta, x upon a. Tan theta, how can we find out? So we'll square this term, we'll get x square upon a square is equal to sec square theta. Okay, sec square theta is 1 plus tan square theta, right? So x square upon a square is equal to 1 plus tan square. Right? Now we'll shift the 1 on the other side. So x square upon a square minus 1 equal to tan square, and then what will be tan theta? Root of this value. So root of x square minus a square upon a square equal to tan theta. Now we have both the values. Let us substitute in our LHS. So we'll have log is equal to, or log of sec theta x square upon, sorry, not x square, x upon a. So x upon a, okay, plus what is tan theta? Root of x square minus a square, okay, divided by root of a square is a, okay, plus c. Now you can see that the denominator is same, okay, so we'll write this as, let us take c as c1, I'll tell you the reason why it is C1. LHS is equal to, so we have LHS equal to log of x plus root of x square minus a square, okay, divided by a plus C1, which can be written as log of x plus root of x square minus a square, okay, minus log of a plus C1, yes, which is, now this minus log of a plus C1 can also be written as another constant, say C. Okay, so as because log of a is basically a constant value, so anything with that with c would be it a constant only. So this will be root of x square minus a square plus c. Okay, that is your LHS. Clear? Which is equal to our right hand side. That's why I've taken C1, because I'm getting one more constant in my equation and putting them together, I've written C. So what did I have to prove? 1 upon root of x square minus a square dx is equal to log of x plus root of x square minus a square plus C. Okay, this was the fifth one. Now the sixth and the seventh one, I'm leaving it up to you because it's exactly same to what we have just solved. That is the fifth one. Okay, but I'm writing down the identities for you, or you can say special integrals for you. The sixth one, okay, so the sixth one is integration of 1 upon root of x square plus a square dx is equal to log of x plus root of x square plus a square, okay, plus c. So you can see that it is exactly same like we did the previous one. Only thing you need to know the substitution. For that you can utilize your red box, or I will give you the substitution here. X is equal to a tan theta. Use this substitution and solve the proof. Okay, this is for the sixth one, and the seventh one is integration of 1 upon x root of x square minus a square, okay, dx is equal to 1 upon a sec inverse x upon a plus c. Okay, now I'll just give you the substitution here. X is equal to a sec theta. Okay, use this substitution and solve the sum. You'll exactly get to this answer. Okay, if you still find it difficult, you can write to me. I will solve it for you separately. Okay, so let's do one thing. Let us put all these special integrals on one page, or you can say together, so that you have them for reference. Okay, the first one was integration of 1 upon x square plus a square. 1 upon x square plus a square is equal to dx 1 upon a tan inverse x upon a. See, as many times as you will write it down, it will be easier for you to remember. I know that it is present in the textbook and I don't need to write it down and it wastes time, but I'm doing it only so that I am encouraging you to also keep writing them down, so that you don't have to refer to any book page or textbook while solving the sums. Okay, let us do this. 1 upon x square minus a square dx is equal to 1 upon 2a log of x minus a upon x plus a, okay, plus c. Third one, integration of 1 upon a square minus x square dx is equal to 1 upon 2a log of a plus x upon a minus x plus c. Okay. Fourth one, integration of 1 upon root of a square minus x square dx is equal to sine inverse x upon a plus c. Okay, the fifth one, integration of 1 upon root of x square minus a square dx is equal to log of x plus root of x square minus a square plus c. This is the fifth one. 6 and 7. Sixth one, integration of 1 upon root of x square plus a square dx is equal to log of x plus root of x square plus a square plus c. Okay, and the seventh one, integration of 1 upon x root of x square minus a square square minus a square dx is equal to 1 upon a sec inverse x upon a plus c. Okay, keep practicing them, writing them so that you remember, find a way to remember them. See, it's not that difficult. If you can check, like you can put two in a group, like the second and third, if you observe, only the signs are interchanged for the denominator. When the signs for the denominator are interchanged, that is x square minus a square, answer is log of x minus a upon x plus a. If it is a square minus x square, then the answer is log of a plus x upon a minus x. Okay, so order will be from here. Okay, if denominator is minus a square, then numerator on the right hand side will have minus a. If denominator is plus a square, then the numerator will have plus signs in the right hand side. Okay, so this is for 2 and 3. Then you can combine 4 and 5, not 4 and 5, sorry, you can combine 5, 6 together. That is, the fifth one is 1 upon root of x square minus a square. Okay, so it's log of x plus root of x square minus a square, right? And 1 upon root x square plus a square is log of x plus root of x square plus a square. There's no difference at all. Just the denominator, whatever is on the left hand side is on the right hand side. Okay? It's plus on both the right hand sides. That's fifth one, fifth and sixth. So second, third is done. 5, 6 is done. We are left with 1, 4, and the seventh one. Let's go to the first one now. 1 upon x square plus a square. That is a basic. If you're getting perfect squares in the denominator, that is with a plus sign, then it is tan inverse x by a. Okay. So this is easy. 1 upon a tan inverse x by a. Do not forget the 1 upon a. Okay. And the fourth one and the seventh one. Now the seventh one is completely different. If you observe, there is an x value outside. Okay, and then there is root of x square minus a square. Okay, so you will know the type from the sum itself, and then you can write 1 upon a sec inverse x by a. Okay, so we'll do sums on these in the next session. Also, there are a few types of sums that we need to go through before, type of integrals I would say, before we go to the next exercise. Okay, so we'll do that in the next session. Now, if you have any doubt in these proofs or any other sum, do write to me. I will solve that for you. Thank you so much.